Every good or service requires a sequence of steps to create. To control it, managers must measure the speed of value creation. Without a standardized metric for processing speed, an operations team is flying blind. Pinpointing the source of an inefficiency within a complex, multi-step system becomes mathematically impossible. System engineers quantify this speed using a specific unit of measurement known as cycle time. Measuring this precise metric is mandatory for any facility. It dictates how a system sets its capacity limits and determines exactly how fast an organization can respond to a customer. Mastering the mechanics of cycle time is the mandatory first step to controlling the overarching output of any operational system. Cycle time is formally defined as the actual time required to complete exactly one unit of work. The measurement boundaries are rigid. The stopwatch starts at the exact initiation of processing, and it stops at the completion of that same specific unit. This is a strictly unit-based track. It requires isolating the time spent on a single item, rather than looking at the broader metrics derived from measuring entire batch outcomes. Academically, this measurement requires a specific assumption. It must be recorded under normal operating conditions. Data skewed by catastrophic machine failures or power outages is excluded from the baseline. Establishing this strict internal boundary isolates the mechanical process from external market noise. The result is a pure metric of systematic efficiency. A cycle time is not a single monolithic block of time. To optimize it, engineers mathematically deconstruct the cycle into its component parts. The first component is value-added processing time. This is the duration where the actual physical or digital transformation of the unit occurs. The hidden second component is waiting time. This block includes inter-process queues, material delays, and administrative holds where the unit sits idle. The conditional third component is handling or setup time. Whether setup time is factored into the final cycle time calculation depends entirely on the specific operational definition or lean framework the facility applies. Because non-value-added waiting time frequently outweighs actual processing time, reducing a system's cycle time rarely means speeding up machinery. It requires hunting down system delays. This measurement translates across industries. The rules governing cycle time on a factory floor apply directly to administrative software. In physical logistics, baselines are highly visible. An assembly line measures 45 seconds to produce a single unit, or a warehouse picker requires exactly 6 minutes to complete one physical pick list. Service operations track human interaction. A retail bank evaluates the 4 minutes a teller requires to complete a single customer transaction. This diagram of an order lifecycle shows how digital processing works the same way. We can track the precise 10-minute administrative window from data entry to digital confirmation across nodes 1 through 3. Standardizing these measurements gives operations engineers a common mathematical language. It allows them to compare mechanical efficiency against administrative efficiency. Regardless of whether the output is a steel beam or a software confirmation, cycle time consistently answers one central operational question: how fast can we repeatedly produce one unit? Single unit measurements are only useful when applied to the systemic flow of a multi-step process. This introduces the bottleneck principle. The single step with the longest cycle time dictates the maximum pace for the entire system. The efficiency of the entire line is entirely dictated by how you manage the waiting times leading into and out of this specific bottleneck cycle. This leads to throughput. Throughput is defined as the total output rate of a complete system over a given period. The mathematical relationship between these concepts is rigid. The cycle time of your bottleneck directly constrains your system's maximum throughput. Optimizing the cycle times of any step other than the bottleneck is an illusion of progress. Throughput only increases when the longest cycle time is reduced. One of the most pervasive operational errors found in both undergraduate classrooms and active supply chains is conflating cycle time with lead time. This workflow chart shows lead time as the customer-facing metric covering total elapsed time from initial request to final delivery. Cycle time is a strictly internal metric nested within that lead time window, executing only after work officially starts. Viewing this on another timeline, cycle time occurs strictly between the nodes where an order is taken for production and the moment it's complete. The lead time bracket stretches far beyond production boundaries, beginning when the order is received until final delivery. This is also distinct from takt time. Takt time is a purely demand-driven target, dictating how fast a unit must be completed to meet customer orders. It is entirely separate from the actual mechanical capability measured by cycle time. Conflating these terms has severe consequences. If you promise a delivery date to a customer based solely on internal machine cycle times, you are ignoring upstream and downstream cues. Doing so guarantees a supply chain failure. Maintaining consistent cycle times in modern operations is difficult. High system variability, like fluctuating material quality or irregular labor availability, instantly inflates cycle durations. Manufacturers also face a specific paradox. Implementing advanced automation often drastically reduces the actual processing time of a unit, but inadvertently increases the setup and handling time required between runs. Simultaneously, the adoption of digital workflows is rapidly compressing administrative cycle times, rendering legacy paper-based systems uncompetitive. Because these variables constantly fluctuate, relying on periodic manual cycle time audits is obsolete. In modern logistics, static metrics are dead. Continuous dynamic cycle time management requires real-time data integration directly from the floor. Cycle time is the foundational measure of internal process speed. It is rigidly bounded from the exact start to the final completion of a single unit's creation. It is a metric governed by the mathematics of system bottlenecks, and it is strictly isolated from the external cues that define customer lead time. For operations managers, the work requires exact diagnostics. You must identify where the real bottleneck lies in your system and aggressively target the embedded waiting times that add zero value to the product. Evaluate your own system architecture. If customer demand suddenly doubles tomorrow, which specific cycle time in your process breaks first? Maximizing isolated machine speed accomplishes nothing on its own. The ultimate goal of operations management is the absolute mastery of continuous system flow.